welcome back. In the last lecture, we concluded our discussion on the trading strategies involving option contracts. We talked about combinations of options with underlying assets and options inter se. Today, we start something new. We talk about the pricing of derivatives, how the values, how does the market value derivatives. That is the question that we propose to address in today's lecture and hereafter. Now, before we get into the pricing of derivative securities, we know that derivative securities are functions of the prices of certain underlying assets. These underlying assets may be stocks or other financial assets, or even non-financial assets for that matter, and there may be commodities, there may be a currency, whatever. The important thing is that the derivative contracts are the functions, the payoff of the derivative contracts are functions of the prices of stocks or other assets. So, we must be familiar with the pricing mechanisms or with the mathematical modeling of the prices of the underlying assets. It is only then that we can move on to the pricing of derivative securities. Once we talk about the pricing of the underlying assets, the pricing of stocks, the contemporary framework, which has in fact been in existence for more than 100 years now, is the framework of stochastic calculus, stochastic processes. So, let us start with a very gentle introduction to the mathematics of stochastic processes. I will confine myself to whatever is essential for understanding the mathematical modeling of stock prices, and then thereon we shall apply them to stock prices, these concepts of stochastic calculus, and continue further to arrive at the derivative prices, end up with the Black-Scholes model, which forms the cornerstone of contemporary valuation of contingent assets. So, before we get into stochastic processes, you see the stock price evolves with time. So, we want to understand the evolutionary dynamics of various types of processes that occur in nature. Basically, on the basis of the behavior of processes or systems in relation to the passage of time, the processes can be, or the systems can be classified into two fundamental categories: deterministic systems and stochastic systems. Chaotic systems are basically deterministic, are essentially deterministic systems, but they are a variant of that which have certain well defined characteristics. I will come back to it in a minute, but for the moment the two fundamental characteristics or the two fundamental systems classified on the basis of their evolution with respect to time are deterministic systems and stochastic systems. Deterministic systems are those systems that if we know the state of the system at a particular point in time, then we can precisely predict the state of the system at any future point in time. I repeat, if we know the state of the system at a given point in time, we can precisely determine the state of the system at a future point in time. Therefore, there are two prerequisites of a deterministic process or a deterministic system. We must be knowing, or we must have knowledge about the initial state of the system, the current state of the system, and we must know how to model the time evolution of the system, so that we can transfer that initial state by virtue of the time evolution mechanism, that whatever physical law or other laws that the system follows, and translate it in time to a future point in time, and thereby obtain precise information about what state the system is going to be at a future point in time. So, two things are necessary: the initial conditions and the evolution equations, which encapsulate the time evolution of the system. Once we know these two, we can integrate them and we can obtain the state of the system at a future point in time. These are deterministic systems or deterministic processes. Chaotic systems are a variant of this deterministic systems, where they are essentially deterministic, but they have the additional characteristic that they are extremely sensitive to initial conditions. In other words, a small fluctuation or a small bit difference, a small change in the initial condition of the system will manifest itself as an exponential blow up in the future evolution of the system. It is sometimes said that a flap of a butterfly wings in Bermuda could cause a cyclone in New York at a future point in time, and in the context of chaotic systems. What essentially is meant is that if there is even a slightest error in the estimation of the initial conditions, the system dynamics would evolve extremely in an extremely different behavior, because the map, the chaotic map is extremely sensitive to initial conditions. So, any small difference in initial conditions manifests itself, magnifies itself exponentially as we move forward in time. So, that is chaotic system. But for our interest is primarily confined to stochastic systems and stochastic processes. Stochastic systems are those systems which evolve in time in not a precisely predictable manner. In other words, they have a certain random component in their evolution. How that random component arises, we have discussed earlier also. It may be due to inadequacies in the measurement of the initial state. It may be due to ignorance of the factors that specify the complete initial state. We do not know what are the various factors or various variables that completely define the initial state, or we are not conversant with the evolution of those factors in time. We are not able to model precisely the evolution of these factors in time, or it could be a combination of all of these. But the basic thing is that there is an element of unpredictability in the time evolution of the system. In other words, given a certain initial condition, given a certain value as of today, as of now, we cannot precisely exactly estimate the value of the system at a future date. These are stochastic systems, they have a certain random component in them. Right. So, that being the case, because the stochastic process evolves randomly in time, we can express a stochastic process in terms of a sequence of random variables. At every point there is an element of randomness in the evolution of the process. Therefore, we attach a random variable to each instant of time at which the system evolves, and as such the entire process can be viewed as a collection, as a sequence of random variables. And these random variables can either of course be discrete, can be continuous, we are coming to that, but the basic thing is they will be indexed in terms of time, because we are talking about evolution in terms of time. Of course, at a very general level we could have other indexing sets also, but for our purpose we shall always assume that this process is indexed in terms of time, because we are talking about evolution in terms of time. Now, there is a very important variant or an important subset of stochastic processes, which is called Markov process. Stochastic process is a general class of processes where the evolution is unpredictable. Markov process is a specific, very specific, well defined class of stochastic processes which has no memory. By no memory, what we understand is, we understand that the next step, given a particular point in time, let us say given a point in time say t equal to t, the next step of the stochastic process t plus 1, what value the stochastic process is going to take at time t plus 1 depends only on the state at which the process is at t equal to t. In other words, now whatever is the prior history of the process is irrelevant to the future evolution of the process. I repeat, let me clarify this. Let us say we are at this point, say t equal to small t, and the next instant of time at which the process is going to evolve is, let us say, small t plus 1. Now, the process is unpredictable, therefore, it can take certain values within a certain sample set at t equal to t plus 1. Now, what value it is going to take would depend only on the state of the system at t equal to t, that is one prior instant. Whatever has happened prior to that, t minus 1, t minus 2, t minus 3 and so on, is irrelevant to the future evolution of the system. This is called a Markov process. In other words, the system or the process has no memory in it. Its memory is confined to the current step, to the current point in time. A Markov process is a process whose memory is restricted at any point of time to the immediately preceding time argument. That is, at t plus 1, its memory is confined to t. So, whatever the state is at t will determine whatever it is going to evolve at t plus 1. Obviously, it would be random, but it would not be affected at all by whatever happens in the history prior to t. Thus, the future state of the system of the process is dependent only on its present state and not on the history of how the process reached this state. In other words, the path followed up to time t is irrelevant. It is only the state at time t which is relevant. Now, what is the implication of the Markov property? The implication of the Markov property will be very clear in the next point. For the moment, the important thing is that the entire stochastic process or the entire evolution of the stochastic process can now be described. If it is a Markov process, it can be described in terms of two quantities: the single time probability P 1, 1 means one point in time, the probability of the system being in state g at time t, state j at time t, that is P 1 j t, and the conditional probability that the system, two time conditional probability that the system goes to state k at time t given that it was at state j in time t 0. So, these two conditions, these two quantities, quantity 1 and quantity 2, completely specify a Markov process. In other words, they completely specify a stochastic process if it is a Markov process. And let us look at this carefully. Obviously, any general stochastic process, not necessarily a Markov process, any stochastic process needs to be defined in terms of the probabilities of the states at which the system is going to be at various instants of time. Let us say we have various instants of time starting from t 1, t 1, t 2, t 3 up to t n. We have indexed our time interval between t 1 and t n as t 1, t 2, t 3, t 4, t n. And now a process is evolving, a stochastic process is evolving starting from t 1, it takes a value at t 2, a random value, it takes a random value at t 3, it takes a random value at t 4 and so on. Now, in order to completely specify this process, we need to have the joint probabilities of the system being in various states at each of these instants of time t 1, t 2, t 3, t 4 and t n. I repeat, in order to completely specify the system, we need the joint probabilities of the system being in various states j 1, j 2, j 3 and so on at times t 1, t 2, t 3, t n, which is given by this expression. This is the n, and this n is the n time joint probability of the stochastic process taking a particular path between t 1 and t n, the joint probability of various points on the path. Now, using Bayes theorem again I reiterate, we are talking about all general stochastic processes, we have not introduced the Markov property still. So, P n is equal to, using this Bayes theorem, this is my left hand side. I can write this in terms of the conditional probability and the probability of the remaining quantity as given in this Bayes theorem. This is called Bayes theorem. So, I write it as P n, J n, T n, the conditional probability of the process being in state J n at time T n, given that it is in state J n minus 1 at T n minus 1 and so on, into the n minus 1 time probability, n minus 1 time probability of the system being in state 1 at time t 1, in state 2 at time t 2 and in state t n minus state j n minus 1 at time t n minus 1, which is given by this. Continuing this process iteratively, we end up with this expression P n j n t n subject to j n minus 1 t n minus 1 j 1 t 1 into P n minus 2 n minus 1 j n minus 1 t n minus 1 j n minus 2 so and so into P this iteration will continue as n minus 1 and then n minus 2, then n minus 3 up to P 2. P 2 is the 2 time probability j 2 t 2 subject to j 1 t 1 and then the 1 time probability P 1, that it starts from state j 1 at time t 1. So, this is simply splitting up the n time probability into its various components in terms of conditional probabilities. This is the joint probability, n time joint probability, and it is being expressed as a product of various n minus 1, n minus 2 and so on conditional probabilities. Now, we come to an application of this, and what happens if the process is Markovian? If the process is Markovian, the process the probabilities do not depend on the history of the process beyond the immediately preceding state, beyond the immediately preceding state. Therefore, P n j n t n subject to j n minus 1 t n minus 1 and j 1 t 1 is nothing but P 2 j n t n j n minus 1 t n minus 1, because all this rest of this stuff does not affect the evolution of this state. That is the definition of Markov property. This evolution portion depends only on this and not on whatever is earlier. Therefore, we can write it as this form, and when we incorporate this into our earlier equation, we find that the joint probabilities in the case of a Markov process can be expressed as 2-point probabilities, 2-point probabilities, 2 time probabilities multiplied by this 1 time probabilities j n minus 1, j n minus 1, j n minus 2, of course, with the respective time arguments t n subject to t n minus 1, j n minus 1, t n minus 1 subject to j n minus 2, t n minus 2. For example, what does this represent? Let me make it clear. This represents the probability of the system evolving from j n minus 2 at t n minus 2 to j n minus 1 at t n minus 1. Similarly, what is this? This is the probability of the system evolving from j 1 at t 1 to j 2 at t 2 and so on, and this is the probability that the system starts at j 1 at t 1. So, for a Markov process, we can write the joint probability of the entire stochastic process in terms of 2-point probabilities as shown here, and the 1-point probability which is given by this expression. Now, we can have two types of stochastic processes: discrete time processes and continuous time processes. Let us first talk about discrete time processes. In discrete time processes, time is assumed to move in discrete chunks, in discrete intervals. In other words, there cannot be any you cannot subdivide time indefinitely. There is a lower bound up to which you can divide a period of time, and beyond that you cannot do that. It is something like a scale, a scale where you cannot split that scale beyond a certain point. So, in discrete time process, time is around to evolve in discontinuous jumps. You have t equal to 0, then t equal to 1, t equal to 2. You cannot have something which is in between these two. Of course, you can index them. You see, if you want to reduce the time interval, you can re-index them. For example, for example, let us say t equal to 0 to t equal to 1 is one day, and you want to convert it into hours. Okay, you re-index them, you put them as 1 hour, 2 hours, 3 hours, 2 hours, 4 hours. But the basic thing, the basic property of these processes is that time has to be taken in discrete points. It's just like a lattice. You can represent time on a lattice where the points are regularly spaced. And there is nothing in between, and the important thing is that the process, when it evolves only at the points on the lattice. It does not evolve, the process does not move, it does not evolve in the interval between any two points on the lattice. It evolves only on the points that constitute the time lattice or the. So, in the discrete time processes are processes where time is taken in discrete intervals. It may be 1 day, it may be 1 hour, it may be 1 minute. That is not the point. The point is it has to be discrete. It is not a continuous flow, like it's a given any two time intervals, you can find a third time interval, that may not necessarily always hold. Okay. And similarly, we have discrete variable processes. As I mentioned, a stochastic process is a process which evolves unpredictably in time. As time passes, as time progresses, the process evolves, but we cannot foresee the precise or we cannot predict precisely how the process is going to evolve in future. Now, that variable which is going to evolve can either evolve in discrete points, it can have a discrete spectrum, or it can have a continuous spectrum. So, if it has a discrete spectrum, then it is called a discrete variable stochastic process. If it has a continuous spectrum, it can take any value between a given interval, say 0 and 1, then it is said to be a continuous stochastic process. Just like time, if you have a discrete variable stochastic process, you can represent it by points on a lattice. Now, let us come to the simplest possible example. The simplest example is you are at the origin t equal to 0. The first time step, which is of length t, but remember it is one step. So, nothing can happen in between. This is hollow, nothing can happen this. This is one time step, but the length of the time step, as I mentioned, can be 1 minute, 1 hour. You can also write it as 1 by 24th of a day. So, that is not the point. The point is that it is one unit of time. Howsoever you have taken that unit of time is irrelevant, but you have to be consistent, of course, on the scale. So, that being the case, you start at t equal to 0, the time there is a unit time interval that is of length t, and in other words, there is one step of length t. After time t, there will be one jump. You will make one jump either up or down. How you decide up or down? Well, you toss a coin. You toss a coin. If you get a head, you jump up, and if you get a tail, you jump down. How much you jump down is also known. You jump 1 meter up or you jump 1 meter down. This is the simplest possible example of a stochastic process, what we call unscaled single step random walk. unbiased, unscaled single step random walk. Unbiased, why? Because the probability of up and down is the same, which is 1 by 2. So, it is unbiased, unscaled, single step, there is only one step, and at the end of that step you are making a jump either upwards or downwards depending on the toss of a coin. Now, let us work out the critical parameters of this. You are at t equal to 0, the first step and the only step that you take is at t equal to capital T. There is nothing, I repeat, there is nothing in between, time is discrete. So, you cannot do anything in between. When this clock strikes t, you make one jump, that is the first time, it is a time step, you make a jump up or you make a jump down. If you make a jump up, you get the coordinate this, and if you make a jump down, you get the coordinates t plus 1. If you jump up, you jump down, you get the coordinates t minus 1. This is 1 meter, this is 1 meter, it can be 1 foot, it can be 1 kilometer, whatever it is, that does not matter. So, now what are the possible values? W1 is the number or the time steps. So, there is one time step. So, we have taken it as W1, t is the length of the time step, that is capital T in this case. This is equal to, I am representing this plus 1 and minus 1. This, you see, this is a random variable now, whether you jump up or you jump down is a random variable, it will be determined by the toss of a coin, which is a random event. So, if you jump up or jump down, the probability in each case is 1 by 2, and I can write this in the form of a random variable, let us call it x1, where x1 can take the value plus 1 and take the value minus 1, each with probability 1 by 2. It can take the value plus 1 with probability 1 by 2, it can take the value minus 1 with probability 1 by 2. What is the mean value? Mean value will be given by 1 by 2 into plus 1 by 2 into minus 1, that is equal to 0. So, the mean value, that is expected value of W1 t is nothing but E of x1, because we are writing it that way, and that turns out to be 0. And what is the mean value of x1 square? What values x1 square can take? X1 square can take values plus 1, and even if x1 is minus 1, it can still take the values plus 1. So, plus 1 into 1 by 2, plus 1 by 2 into plus 1 by 2 into plus 1, that makes it x1 square is equal to E of x1 square is equal to 1, and sigma 1 square is equal to E of x1 square minus E of x1, which is equal to 1 in this case. So, the critical parameters are the mean is 0 and the variance is 1. These are the important things. The variance is 1 and the mean is 0. This is the simplest possible random process. This is called a single step random walk. Let us now increase the number of steps. Let us now look at a 2-step random walk, same parameters, 2-step random walk. What we have done now is we still have the time interval 0 to t. Now, instead of having a single step in 0 to t, in other words, instead of your jumping up and down only at time t equal to t equal to capital T, that was a single step, that is the only thing that you could have done. Now, what happens is you make 2 jumps. You make a jump at t equal to t by 2, capital T by 2, and you make another jump at t equal to capital T. In other words, the single step has now been replaced by 2 steps, but within the same overall time frame. The overall time is still t, but you have now split up 0 and t into 2 discrete intervals. I continue, I emphasize that they are still discrete. 0, you cannot do anything between 0 and t by 2. You will make your first jump at t by 2. It will either be up or it will be down. You will toss the coin, and if you get ahead, you will jump to plus 1. This will be plus 1 as it is given here, and this will be minus 1 as it is given here. If you get ahead, you get plus 1. If you get a tail, you get minus 1. Then you from so so at t equal to t by 2, where will you be? You will either be here or you will be here. You will either be at point P or you will be at point Q, either at P or at Q. Now, we do not know whether you will be at P or Q, but you will be either at P or at Q. Now, from here you make a second jump. You make a second jump at t equal to capital T. If you are at P, you make a jump to either, let us call it C, or you make a jump to B. These are the only two possibilities. If you get a head, you will jump to C, and if you get a tail, you will jump back to B. From here to here, nothing will happen. After t by 2, that is at t equal to capital T, you will make a jump either upwards to C if you get a head, and if you get a tail, you will jump back down to B, and obviously the coordinates are +2 for the up jump and 0 for the down jump. Similarly, if you are at Q, then the up jump will bring you to B and the down jump will bring you to A. In other words, if you get a head from Q, you go upwards to B, and if you get a tail from Q, you get downwards to A. I emphasize once again that this jump will take place at t equal to capital T. It will not take earlier. Time is discrete. The first jump takes place at t equal to t by 2. The second jump takes place at t equal to capital T. Let us see the parameters, how they work out. Now, we have got two jumps. So, we have W 2 t. We are working out the parameter values at time t equal to capital T. So, we are writing capital T here. This is the point at which we are working out the parameters value, the mean and the variance. So, W 2 t is equal to where you were after the first jump plus where you moved from the first jump. This is where you were at the end of the first jump, and then where you moved at the end of the second jump. This is given by x 2. x 1 represents the first jump, x 2 represents the second jump. Clearly, it can W 2 t can take the values +2, it can take the value 0, and it can take the value -2. These are the three values that W 2 t can possibly take: +2, 0 and -2. The expected value is clearly 0, and the expected value of W 2 square is given by. Now, the important thing to note here is that this 2 e x 1 x 2, because they are independent of each other, they are uncorrelated. So, I can write it as 2 e x 1 e x 2, and we know that this is 0 and we know that this is 0. So, this term does not contribute anything. This term we have already found as 0 as 1, and this term also we found as 1. So, this whole term works out to 2 as given here. This square plus this square is 2, and this term is 0. So, it does not contribute anything, as a result of which the variance, if you look at it, the variance is 2 minus 0, which is equal to 2. So, for the two step binomial tree, the mean is 0, the mean continues to be 0, but the variance has changed from 1 to 2. This is important. We will continue after the break. Thank you.